Sperm concentration estimates can be made quickly and easily using the Caris densimeter. 9 milliliters of 2.9% sodium citrate should first be pipetted into the densimeter. After carefully mixing, 1 milliliter of raw semen is added. The densimeter is then covered with a small piece of parafilm and inverted 2 to 3 times in order to mix well. To estimate the concentration, the densimeter is placed in front of a solid white surface or paper. Holding the unit at arm's length at eye level, the scale is observed. First, the markings for the printed numbers, 60, 70, 80, and so forth, are identified. Look for the highest number that is clearly readable, such that the next highest number is cloudy. As shown here, the mark for 50 is clear, while that for 60 is cloudy and not readable. Next, look at the half-scale number markings. For example, 65, 75, and 85. The line for 55 is clearly readable, while for 60 it is not. The answer is then 55. Using the chart supplied with the densimeter, the estimated concentration is determined. In this example, the concentration is 265 million sperm per milliliter. The densimeter should be thoroughly rinsed with clean water in between uses. The third method for determining sperm concentration is using a special microscope slide called a hemocytometer. This technique requires that you first dilute a sample of the raw semen very accurately, usually at a ratio of 1 to 200. The simplest and fastest way to make this dilution is with a Unipet semen dilution system. This system consists of a vial of pre-measured diluent and a special transfer pipette known as a capillary tube that also serves as the measuring device for the semen. Place the vial on a counter in front of you. With the bullet-shaped plastic cap of the capillary tube, pierce the seal in the neck of the vial. Remove the plastic cap from the capillary tube and set it aside. Fill the capillary tube by holding it into the raw semen as horizontally as possible. This generally takes only a few seconds. Remove the capillary tube from the semen and, holding it horizontally, check to make sure the tube has filled to its full length. If it is not full, place the end back into the semen until it fills. A very small error in the volume of semen in the capillary tube or sampling an ejaculate that is not sufficiently mixed will result in a tremendous error in determining the sperm concentration of the ejaculate. Wipe the end of the capillary tube that was in the semen with a tissue, being very careful not to touch the open end of the tube. Hold the vial of dilution media in one hand and squeeze the sides in to displace some air. Place the capillary tube into the neck of the vial and push down firmly to seal the collar of the capillary tube holder onto the neck. Gently relax some of the pressure on the vial to draw the semen out of the capillary tube into the dilution media. When the capillary tube is empty, squeeze the vial to force some dilution media back up the capillary tube. Be very careful not to force too much liquid up and out of the tube. Allow the media to be drawn back into the vial. Repeat this procedure once or twice more to be sure you have removed all of the semen from the tube. Remove the tube from the vial and reverse its position on the neck of the vial so the capillary tube is now pointing outward. It will now serve as a pipette to load the hemocytometer chamber. Gently but thoroughly mix the semen and media in the dilution vial. Expel several drops of the diluted semen into a tissue. Place the hemocytometer in front of you with its special cover slip in place. The cover slips are made specifically for a hemocytometer and are perfectly flat. Load each side of the counting chamber by placing the end of the pipette in the groove of the chamber and gently squeezing the vial. The diluted semen should fill the chamber completely. It is important to completely fill but not overfill the chamber. Once both sides of the chamber are filled, gently place the chamber aside for at least 5 minutes to allow the sperm cells to settle onto the surface of the counting grid. Do not allow the chamber to dry out during this waiting period or during counting. After allowing the sperm to settle, place the chamber on the microscope stage for counting and focus on one of the grids at 200 times magnification. A phase contrast microscope will enhance your ability to visualize and count the sperm cells. Focus on the grid where there are 25 large squares bordered by triple lines. Each large square is divided into 16 small squares. You will be counting all of the sperm cells in 5 of the large squares, using the small squares to index your movements across the grid system. Develop a system for counting and do it the same way every time. For example, starting in the upper left corner, count clockwise the 4 large squares at the corners, and then finally count the center large square. When counting individual sperm cells within a large square, work through the 4 rows and columns of smaller squares in a pattern as well, such as starting in the upper left corner and count in a serpentine pattern from left to right. Then down 1 row, right to left, down 1 row, left to right, and so on. Count all sperm cells touching the triple lines on 2 sides of the large squares, such as the top and left. But do not count any sperm cells touching the opposite 2 sides. When counting sperm cells, count heads only, ignoring tails completely. For convenience, a hand tally counter may be used. When you have finished counting one grid, 5 large squares, record the number from the tally counter, reset it to 0, and continue on to the next grid. Calculate the average of the 2 counts. The formula for determining the number of cells per milliliter is the number of cells counted times 50,000 times 200 equals sperm per milliliter. In this formula, the factor 50,000 compensates for the area of the chamber counted, and the factor 200 represents the dilution made using the Unipet system. For example, if the 2 counts are 61 and 58, the average is 61 plus 58 divided by 2, which equals 59.5, or rounded to 60. Then, 60 times 50,000 times 200 equals 600 million sperm cells per milliliter of ejaculate, or 0.6 billion sperm cells per milliliter. In scientific notation, 0.6 billion is converted to 0.6 times 10 to the 9th sperm per milliliter. This number should be recorded. The total number of sperm cells in the ejaculate is determined by multiplying the volume of the ejaculate in milliliters by the sperm concentration per milliliter. For example, 165 milliliters times 0.6 times 10 to the 9th sperm per milliliter equals 99 times 10 to the 9th, or 99 billion sperm in the ejaculate. For improved accuracy, additional dilutions per sample and/or additional chambers per sample can be prepared and evaluated. Most laboratories use a photometer to determine sperm cell concentration. Minitube's SpermaQ is a specially designed photometer for this purpose. The photometer allows for a rapid, accurate measurement of sperm cell concentration. Within the unit, a beam of light is passed through a specific sample size, and a photodetector measures the amount of light that is transmitted or absorbed by the sample. In the case of ejaculates, the photometer is typically calibrated using another counting system, such as a hemocytometer, and a calibration curve is established which equates different sperm cell concentrations with equivalent transmittance or absorbance values.